Man, it's so hot out here. The sun is so bright. And that might be uncomfortable for me, but it's a good thing for all of these solar panels. The more sunlight these panels can collect, the more energy they make. Although, now that I think about it, I wonder how engineers make sure solar panels collect plenty of sunlight, even as the sun moves in the sky. Hi, I'm Annika, a second-year student studying creative technology and design at CU Boulder. And today, let's take a look at how engineers ensure solar panels are as efficient as possible. This is a solar panel, although that term isn't very specific. The term solar panel can refer to many devices that capture the sun's heat. Today, we're specifically talking about photovoltaic panels, shortened to PV panels, which are devices that turn the light from the sun into electricity. When we're making energy using PV panels, we want to make sure our panels are working as efficiently as possible. For a panel to be working efficiently, we want it to turn as much sunlight as possible into usable electricity without wasting energy in the process. And to maximize how much sunlight a PV panel turns into energy, we need to maximize the amount of sunlight that panel collects. So we should just be able to point a PV panel directly at the sun, right? Not quite, because the sun is constantly in motion. If we point our panel right at the sun right now, it won't be pointed directly at the sun in an hour, or in a day, or in a week. So, to maximize efficiency, we need to understand how the sun moves. The main motion we see from the sun comes from the fact that the Earth rotates. As Earth rotates, the sun rises in the east and sets in the west, in a cycle that denotes days. We call when the sun is directly in between east and west local noon, and exactly when local noon happens changes as you move around the planet. The other kind of motion of the sun is harder to notice because it takes the whole course of a year. You see, the Earth rotates on a tilted axis. The tilt doesn't change as we revolve around the sun. On a day we call the March equinox, we're in a position in our orbit where drawing a direct line from the sun to the Earth would put that line at the equator. If you were standing on the equator at local noon on the March equinox, the sun would be at your zenith, meaning it would be directly above you. If you weren't at the equator, the sun would be at the reverse of your latitude. So, if you were at 40 degrees north, the sun would be 40 degrees south of your zenith, and vice versa. As we orbit the sun and move into June, the direct line from the sun moves northward, until we eventually reach a day called the June solstice. At this point, the direct line from the sun is as far north as it will get, pointing at a latitude of about 23.45 degrees north. In the northern hemisphere, you might call this day the summer solstice, as this solstice happens during the summer. In the southern hemisphere, you might call it the winter solstice. If you stood at the equator at local noon on the June solstice, the sun would be 23.45 degrees north of your zenith. If you were anywhere else, you could calculate how far north or south the sun would be of your zenith at local noon pretty easily by drawing a quick picture. You can mark your latitude and the latitude of where the sun is pointing. Then, based on how far away each is from the equator, and whether you're on the same side of the equator as the sun is pointing, you can do some quick math and determine where in the sky the sun is. We continue orbiting into September, and the direct line from the sun moves back southward, until eventually reaching the equator again, just like it did at the March equinox. Similarly, we call this day the September equinox, and the sun is in the same place in the sky as it is during the March equinox. We keep orbiting into December, and the direct line from the sun moves south of the equator, until we reach a day called the December solstice. At this point, the direct line from the sun is as far south as it will get, pointing at a latitude of 23.45 degrees south, like the reverse of the June solstice. In the northern hemisphere, you might call this day the winter solstice, and in the southern hemisphere, you might call it the summer solstice. We can use a drawing to calculate where the sun is in the sky anywhere during the December solstice as well. And in fact, as long as you know where the sun is pointing on any given day and the latitude of a place, you can calculate where the sun is in the sky at that place at local noon. And finally, we keep orbiting until we're back at the March equinox, and it all starts again. So the sun moves a lot, both over the course of a day and the course of a year. If the sun is always moving, then where should we point our PV panels to make them work as efficiently as possible? Well, let's see. When it comes to where we should point our panels for maximum efficiency, the ideal answer is directly at the sun. But that would require a dual-axis PV tracking system, meaning a panel that could move on two axes and follow the sun east to west and north to south. Some PV panels are dual-axis, but what if we only had a single-axis tracking system, meaning it could only move on one axis? We'd want to track the sun's movement during the day, since that changes much more rapidly than over the course of a year. But where should we point it north to south? Or what if we wanted our panel to be fixed, meaning it doesn't move at all? Well, the answer is pretty simple. Point our panel at the average point of the sun's movement. During the day, the sun moves from the eastern horizon, which we'll call negative 90 degrees for the moment, to the western horizon, which we'll call positive 90 degrees. What's the average between 90 and negative 90? 0, which just so happens to coincide with where the sun is east to west at local noon. So, if our solar panel isn't tracking the sun's east to west movement, we want our solar panel to point straight in between east and west. During the year, the sun moves from 23.45 degrees north of its position on the equinox, or positive 23.45 degrees, to 23.45 degrees south of its position on the equinox, or negative 23.45 degrees. And once again, the average between 23.45 and negative 23.45 is 0, which coincides with where the sun is at local noon on the equinox. So, if our solar panel isn't tracking the sun's north to south movement, we want it to point toward where the sun is in the sky on the equinox at local noon. If we're designing PV panels with moving systems, we need to make sure the extra energy collected from the moving system is greater than the energy required to operate the system. Otherwise, the system would be wasting energy, and our panel would actually be less efficient than a fixed panel. An example of a PV panel with a moving system that is efficient is the Nellis Air Force Base in Nevada. The panels here have a single-axis tracking system and track the sun across the day from east to west. And thanks to this system, they produce about 30% more power than they would if they were fixed. So while fixed panels are easier to design and install, well-designed single or dual-axis tracking systems can improve efficiency immensely. Photovoltaic panels are a great way to get energy. PV panels don't cause pollution when making electricity, and the sun is a renewable energy source, so gathering energy with them doesn't hurt the environment. In order for us to use PV panels, we need engineers who understand how to make them run efficiently. And now you know the basics of how the sun moves through the sky so you can make PV panels run efficiently, just like a solar engineer. I'm gonna go find an ice cream stand or something to cool down. Thanks for watching, and until I see you again, keep on exploring the bright world of engineering. Check out the full lesson on Teach Engineering, then use what you learned in the associated activity, A New Angle on Photovoltaic Solar Panel Efficiency.